Right, well, I'll make a start then. So, when it comes to pronouncing names that are not English, I tend to say it fast, like putting off a band-aid, so I don't offend anybody. But we have Scheel, which will do, I suppose. So yes, fresh from Bristol, and then Cardiff, and then where else before then? Glasgow, and back home to Netherlands. So you've been all around, so thanks very much for swinging by King's and giving us a talk on equivalence testing. So yes, so briefly about I'm sure you'll go into a bit of famous stuff yourself, but so you did your psychology at Heidelberg and research methods at Glasgow, and then you kind of decided that replication crisis is the place to be, and now you're with Daniel Lankins, who's a hero of mine, and yes, and doing all sorts of exciting stuff. So I'll leave the floor to you, and I won't try any further. Hopefully that will work,
yeah.
But otherwise...
Yes, we'll make it work. Right. Thank you so much for having me. Thanks for the introduction. It's an absolute pleasure to be here. Yeah, as Sam said, I'm currently doing my PhD at the University of Eindhoven in the Netherlands together with Daniel Lankins, and we're working basically on, the goal is to improve research practices in psychology in particular. And I have a background in psychology. Actually, before this PhD, I started another PhD in developmental psychology in Munich doing infant research, and eventually quit and switched to the new open science stuff, partly because doing infant research can be quite frustrating when you realize how poorly fit the methods are to actually find out anything meaningful, and it's very difficult to do to collect the large samples that you would need to do science well. But I'm having a lot of fun now in my new PhD. One of the things I'm focusing on in particular is looking at how open science reforms like pre-registration and registered reports work in practice, if they actually, like what effects they have and what side effects they might have, and so on. What I'm going to talk to you about today is something that my supervisor Daniel Lankins has been working on, equivalence testing, and very early in my PhD we wrote a tutorial paper about this together. I think it can be a very useful method, in particular for psychologists who aren't used to using this yet. So what I will talk to you about today are so we have two papers on this now. The first one is a tutorial paper in AMS. So the talk is sort of the advertisement for this paper. I think the paper is also quite accessible, and I hope that I can give a good introduction to this today. We also have a second paper that compares equivalence testing with Bayes factors. If you're interested in that, we can go into a little bit of detail later, but my talk is going to focus just on to introduce the method in general. My slides are online if you're interested. I also put the link up later on the last slide, so you can see that again. Okay, so briefly, why equivalence testing? What is the problem? So, as I guess most of you are aware, is that what we tend to do or the most used statistical method in psychology, at least, is null hypothesis significance testing. So the way it works is that you usually set up a null hypothesis of no effect that says the effect is exactly 0, and then we test that. And our alternative hypothesis, which is usually our research hypothesis, so this is what we think is true, or what we want to know if it's true, is that the effect is not 0, it's something else. It's larger or smaller. So now if we test the null hypothesis, we find a significant result. If we have a user alpha level of 5%, we can reject the null hypothesis and are very happy, because it means presumably that our research hypothesis was actually correct, so the effect is not 0. But if we get a non-significant result, it's quite unclear what that actually means. So it could mean that the null is true, or it could mean that we didn't have enough power to detect an effect that exists, that is not 0. So the nice thing about frequentist statistics in general is that we can control our error rates. So if we have a significant result, we know how often we would be wrong to assume that the null is false if it is actually true. So if we live in a world where the null is true, we would only get a significant result of % of the time and not more. So that's a nice thing to know. That's very handy. The problem is for the other case, where we don't have a significant result, we might also make an error. So there might actually be an effect in the real world that we're missing, but we don't know how often we would make that error. And to make that so this is the problem basically that equivalence testing is focusing on. So to make that a bit more clear, is basically that the absence of evidence is not the same as evidence of absence. So if we conclude whenever we have a non-significant result that there is no effect, our error is the beta error, so this is 1 minus the power that we have. Problem is that the power we have depends on how big this true effect is. So if we make that error, it means we live in a world where there is a true effect that's not 0, right? And the problem is we don't know what exactly that effect is. And our error depends on how much power we had to detect that effect. And to give you some example of what that can mean in the real world is, so this is like the standard case, the inferences we can draw. We have a significant result if we use an alpha of 5%. We reject the null. So we say, significant result, we're pretty sure the null hypothesis is wrong. But now we have a non-significant result, our p-value is larger. If we have here I have an example of a two-sample t-test. So if we have two groups, each with 20 participants in them, and run a simple t-test, we could get an observed effect as large as a cohency of 0.62, and this observed effect would not be significant in this sample. So if we get exactly this test result, it would never be significant with the sample. So we don't know what the true effect would be in that case, but this is a pretty hefty effect size to miss, I think. So if we, in this scenario, say the result is not significant, therefore we conclude the null hypothesis is true, that doesn't seem ideal, right? So if we increase our power, if we have a larger sample, for example, we have a sample size a group size of 50, so a total sample of 100 people, we could still miss an effect as big as 0.39. An observed effect size of 0.39 would never be significant with the sample. If we up it to 100 people per group, we would still miss an observed effect, or an observed effect of almost 0.3 would still not be significant. With 200 per group, it's 1.9. 500 per group, it's 0.11. With 1,000 per group, it would be 0.08. An observed effect that would not be significant even if you tested 2,000 people. So in all of these cases, basically, whenever you make this inference, we act as if the null is true because we didn't have a significant result. It could always mean that there's still a true effect that you're actually missing just because you didn't have enough power. So essentially it means, does a non-significant result falsify your hypothesis? So assuming your research hypothesis is that the effect is not 0, the effect is something else but 0. Can you ever really know if you were wrong, if you think the effect is not 0? Because you could always say, well, we didn't get a significant result, but we didn't have perfect power because perfect power doesn't exist. So maybe the effect is just smaller than we thought, and you'll never be wrong. Which is presumably why this method has been so popular in psychology, because it's a great tool to never be wrong. Okay, so equivalence testing can offer one solution to this problem. So what we cannot test is if an effect is not 0, because it basically means that we would assume it can only be exactly 0 with no variation at all to ever reject this hypothesis. But we can test if an effect is larger than something that's the smallest effect that we would care about. So let's say the effect has to, we don't care about super tiny effects. So is what we found sufficiently large for us to take it seriously, basically? So the smallest effect that we would care about we call this the smallest effect size of interest, or the SESOI. It's basically a way of you to get around this problem of testing if it is anything but 0, because that's impossible to do. So you make it a bit more specific. You say it has to be at least as large as something, and that we can test. So now the nice thing about equivalence testing, I'm now going to go into how this works statistically, is that it's a really simple method. It's statistically really, really easy to do. It has a bit of a catch that I will get in later. So this is how we usually test null hypothesis. So a null hypothesis significance test, NHST. If we have a point null, so a two-sided test, the null hypothesis effect is exactly 0, and our alternative, so H1, is it's either smaller than 0 or it's larger than 0. And so we test against the null from both sides, basically. It's a two-sided test. What we can also do is do a one-sided test, where we now say our null hypothesis is not just a point, but it's anything, for example, 0, anything smaller. So we don't care about negative effects, we only care about positive effects. So now we only test against the null from one side. And this is already a nice thing to do because you have more power. You have, you can sort of double your alpha to have the same alpha error, or you can divide your p-value by half basically to get at that error. And now what equivalence testing is basically just a variation of one-sided tests. It's two one-sided tests. So the statistical procedure is called TOSTER, two one-sided tests. And what we do is we say, okay, here's 0. We have the smallest effect size of interest. And you put a bound here, which is our smallest effect size of interest, positive one. And then we have smallest effect size of interest on the other side, like negative, if that is what we say. It has to be at least as extreme as this. And now we just flip it around. So we say, we test if it is smaller than the negative SESOI, or if it's larger than the negative SESOI. So we just flip our null hypothesis and the alternative, so we can test this. The idea is that you don't just do this instead of a null hypothesis test, but you can do it in addition to it. So if you, for example, saying you don't find that it's significantly different from 0, you can still test if it's significantly smaller than any, or significantly less extreme as what you would care about, basically. If it's somewhere in here, and if you can reject that it's here, or you can reject that it's here. And this is basically, these two one-sided tests are statistically exactly the same as a one-sided test that you would do against 0 otherwise. You can do a test against any number, any test against any number you want, basically. And so you could also, I'm not going to go into this now. Okay, I'm going to show you a few examples of how this would look like. Oh yeah, so we will basically say, in effect, is statistically equivalent if it falls between these bounds. If it's in here, we can reject that it's smaller than this, larger than this. So we can reject that it's more extreme. So basically, all you need to do is define your SESOI, smallest effect size of interest. Then test against the negative SESOI and against the positive SESOI, two one-sided tests. You can also do this visually with a confidence interval, just seeing if a 90% confidence interval falls between these bounds, if your alpha level is 5%. And I will explain why it's a 90% confidence interval, not 95% in a minute. And that's it. So very, very simple. So to look at some examples, this is a visualization that you get from an R package you wrote called TOSTER. To do this in R, we have 0 here, and we have these two dashed lines, which are our equivalence bounds. So basically the SESOI, positive and negative SESOI. Now we have our effects, observed effect estimate here, and we have two confidence intervals. We have this thicker line, and we have this thin line. The thick line is a 90% confidence interval, and this is what we use for the equivalence test. The thinner line, the wider one, is a 95% confidence interval, which we use to test against 0, because we can do both things. So first, we check if we test against 0. The 95% confidence interval overlaps here that's the case. So he would say, what we can do is we can reject the hypothesis that our effect is smaller than this, and we can reject that it's larger than this. So you can say it's somewhere in here with a fixed error rate. And that's a nice thing to do, I think. Now the reason why it's a 90% confidence interval and not 95 is because it's two one-sided tests. And if you do a one-sided test, you can basically double your alpha, so to say, to get the same error rate. So in a normal one-sided test, you would also use a 90% confidence interval, not 95%, because you basically put all your error on one side. But you would say we do two tests, right? So shouldn't it, doesn't that accumulate? It doesn't. We don't have alpha accumulation in this case because both one-sided tests, so the test against this bound and the test against that bound, they both have to be significant for you to say it's equivalent. It's not an either or. It's not like if it doesn't overlap with this, I will make this decision. If it doesn't overlap, and independently from that, I'm looking at the other bound. And that's why those two tests basically don't interfere with each other. So another example. So in this case, again, we have an effect size estimate here. The two confidence intervals, first looking at the wide one, the 95%, it overlaps with 0, so we can't reject the null. And now the thicker line, the 90% confidence interval that we used for the equivalence test, that overlaps with the lower bound. So we cannot reject that the effect is more extreme than the smallest effect size of interest. So what this would mean is basically both tests are not significant. So we can't reject the null. We also can't reject the SESOI. It means the result is basically inconclusive. We don't know exactly what's going on. It probably means that we need more data to basically make these confidence intervals more narrow. Another example here. This looks funny. You can't even differentiate between the two confidence intervals because they're so narrow, which is because there's an enormous amount of data in that thing. I think the sample size is over 1 million or something. This is an interesting case, and all these examples I gave are from real data, real cases. So here, again, we first test against 0. Clearly this is significant. This is a significant effect, not 0. But it also doesn't overlap with our equivalence bound, so it's also equivalent. So what this means is that we can say this is a non-zero effect, but it's an effect that's too small for us to care about, which I think can be quite interesting, especially theoretically. If you say our effect, we would predict an effect that is at least as large as something, and now you can see it's definitely smaller. That's a nice thing, especially because some people argue that in real life effects are never exactly 0, or almost never exactly 0. So testing against 0 is kind of trivial. This is a nice way to get around this. See, okay, it might not be 0, but it might be too small to be meaningful. Oh yeah, and also in this case I should say the confidence intervals are actually not 90 and 95%, but 99, 99.5, because the alpha level used here was 1%, not 5%. So even though these should be wider than usual, they are so tiny. Lots of data is nice to have. Okay, so to do this in practice, there are 3 software options that you can currently use. There's an R package that Daniel wrote called TOSTER. There's jamovi. Does any of you know jamovi? Yeah. Has anyone of you heard of JASP? Maybe? So if you know JASP, jamovi is basically exactly the same. It looks the same. That's because the same people, same software developers made it. And it's point and click software. It's very easy to use. Also, if you're familiar with SPSS, for example, something like that is easy to use. And there's an Excel spreadsheet. The types of tests that are available are unfortunately a bit limited. So our package has t-tests, correlations, meta-analysis, and proportions tests. So it doesn't have ANOVAs, for example, yet. This is a very popular request. It's a bit difficult to implement, apparently, but people are working on it. What you can always do is basically whenever you can calculate a confidence interval, you can do an equivalence test. And you don't need the software because you can just basically see if the equivalence test does not overlap with your bounds. Now, I'm just going to give an example of how this looks, what this looks like in R, because it's really super easy to use. So this is an example for a two-sample t-test. You just install the package, load the package, and then here you could just use the summary statistics to do this. You have the mean of the first group, the mean of the second group, standard deviation of the first group, standard deviation of the second group, sample size of the first group, sample size of the second group, and then you define your equivalence bounds, the lower bound and the upper bound. And this is, you can do this in Cohen's d, but you can also use raw effect size bounds. I'm going to talk a bit about this in a minute. And you could also pick different alpha levels, 34 is 5%. And this is really all you need to throw in there. You get an output that looks a bit overwhelming here, but you also get a visual output. So the important thing is here you get the equivalence test result. The equivalence test was not significant in this example. You also get the null hypothesis test result. Null hypothesis test was also not significant. And this up here is basically just a breakdown of all the numbers. So what you can see is that actually one of the two one-sided tests was significant against the upper bound, but the one against the lower bound was not. So that means the whole test is not significantly equivalent, so to say. This is the visualization you get as an output. So like the ones you saw previously. So we see both of the confidence intervals overlap with zero, and with one of the bounds. So this is inconclusive. This is actually some of my old data from when I was doing infantry research. So this is a visualization of why it's frustrating, because it is hard to get and very noisy, and you don't learn a lot. Now, what you notice here is the bounds were entered in Cohen's d, right, in a standardized effect size, and the bounds are used for 0.5. You see that the x-axis here looks different, and that's because the x-axis in the visual output you get is always in raw mean difference. And Daniel did that because he wants people to think more about raw effect sizes, so it's a little troll that he put in there. And this is actually quite interesting because it might often be nice to think about raw effects, and finding the smallest effect size of interest might often be easier in raw effects than in standardized effects. Because standardized effects also have something going for them, of course, but they're more interesting for really comparing distributions of different groups, right? But sometimes really the raw difference, for example, the actual behavior basically can be more interesting. Sometimes even the difference in variance can be interesting and meaningful. And so you could get, in two different studies that test the same thing, you could have the same mean difference. So on this scale, the observed effect would be at the exact same point. But you could imagine that the variances are very different in the two tests, for example, because one study was done under very noisy conditions and the other was done under extremely clean conditions, for example, or because it was fraudulent, maybe. That variances are very small, and then the standardized effect in Cohen's d would be way bigger than for the raw effects. And that can sometimes be informative, so it's just a little nudge to start thinking about these things. And you can enter raw effects as the bounds. So you can do that or the standardized effect size, whichever you prefer. So this is what it looks like in jamovi. This is the surface. So if you've seen JASP, it looks very similar. The TOSTER package is not pre-installed, but it's you can add it. So you just need to go to this modules tab here, to the jamovi library. You will see that you can download the TOSTER add-on. And if you've done that, it will, it appears here, so you have it here, and then you can pick your test. And it's really self-explanatory to use. It's very simple to use. Okay, so now this is, as I said, the statistics are very simple. And the actual problem, I guess the actual catch of this, is how do you get your smallest effect size of interest? this is very nice to gloss over and say, hey, look, this is super simple, just use this, and then people try to use it, and it turns out this is actually quite tricky. Okay, so there are different ways of finding your smallest effect size of interest or justifying it. And doing that is really important because it means this is what you test against, right? This is basically the statistical question you ask. So if your smallest effect size of interest is arbitrary, then the answer the test gives you is arbitrary as well. So this is really a really crucial point. So basically the ideal ways of going about is that you have a prediction of a theoretical model. So you say your theory would say that the effect should be in a specific range or something, or it has to be larger or it has to be smaller than something, because otherwise it would be something different, some other process that is not the one that you were actually looking for. So this is, in my opinion, the holy grail. Unfortunately, many psychologists find that the theories they work with don't allow them to do this, because theory is so underspecified and so vague that it's often really difficult to get there. Another option is just noticeable differences, which I think is quite nice. So we have one example in our tutorial paper that I really like. So this is a study in evolutionary psychology. The idea is that apparently women's facial color slightly changes across the menstrual cycle. So there's more facial redness during the fertile phase. And the question is if that is a signal that potential mates can pick up and sort of see if a potential partner is fertile. And so they found that these facial color, these changes in facial skin color do exist, they are measurable. But they also found that they are so subtle that the human visual system can't reliably pick them up. So so this would be a nice way to justifying your smallest effect size of interest, because if this is, if the change that's actually happening is supposed to be sort of theoretically meaningful for you, like if it's supposed to be a signal, it has to be detectable, right? And if you can determine what's detectable, you can use that for your smallest effect size of interest in this case. If you don't have that, there are like more sort of subjective ways of justifying your smallest effect size of interest. You can use benchmarks like medium effect size. I don't recommend this at all, in particular because of what I just said. Like if this is an arbitrary decision, like we just say a moderate effect size, because Cohen at some point said 0.5 is a moderate effect size. This is exactly the inference you can draw. It's like the effect might be smaller than what somebody at some point called a moderate effect size, and it's completely unclear what that might mean for you. You could base it on previous studies. So for example, you could look at a meta-analytic effect size estimate of something that's closely related to what you do. Maybe even better, in this case, looking at the lower end of the confidence interval of a meta-analytic effect size, because you want to have the smallest possible version of this. Another interesting, although slightly tricky solution is the power that a statistical power a previous study had. One suggestion by Uri Simonsson is the small telescopes approach. This was like a suggestion from him for designing replication studies and what sample size you should use in direct replication. And he suggested that you should power for an effect size that the study you're replicating had 33% power to detect. That's also a bit arbitrary. This is just what Simonsson says. Another thing you can do is look at the critical effect size. So the effect size the previous study had 50% power to detect. I find that a bit more interesting because 50% power means this is the smallest effect you could possibly detect. Like what I showed in the beginning, the observed effect that you had 50% power for is the only, or the effect you have 50% power for. It's the smallest observed effect that would be significant in your study. Anything you have less than 50% power for will never be significant. So you could say, these people designed their study in such a way that they had 50% power for this effect size. It means that they couldn't possibly have cared about smaller effects because they knew beforehand, or they should have known beforehand, that they couldn't detect them. So this wasn't important for them. So I will just say this is also not important for me, maybe. Or of course you could use sort of other standard power benchmarks. I think this can be interesting in some cases. Oh, sorry, this was what I said previously. So defaults are a bit tricky because they don't just tell you what is interesting or meaningful. The power approach can be interesting, but it's basically assumptions about someone else's theory, although it can in practice often mean also somebody's statistical education, because if you look at the psychology literature in particular, power analyses are rarely done, and if they are done, they are not very well justified. So people might just not have noticed what they had power to detect, what the effect size were that their study could never have picked up on. So you're basically accusing them of something that they weren't aware of, and it's not necessarily a theoretical argument. Yeah, as I said before, your result is only ever as meaningful as the bounds you test against. Now, one thing that I also find an interesting option is what I've shown you before is an equivalence test as saying, okay, I define my smallest effect size of interest, and now I'm putting one equivalence bound at the positive smallest effect size of interest and the other negative smallest effect size of interest, so symmetrically around 0. You don't have to do that. Maybe as you saw in the R example I gave, you can enter any number for the bounds that you want. So the equivalence range, basically, or the bounds, they can be asymmetrical. They can also be, one can be identical with 0. Or you could, for example, say, I will use this to test a range prediction, which I think would be probably the strongest use. So saying, I have a prediction that the effect should be in a specific range. So, I don't know, between, say, Cohen's d of 0.3 and 0.4, something like that. It's a completely arbitrary example. You could set your equivalence bounds to these two numbers and see if the effect falls between that, and if you can reject anything that is outside of that range. That would be, I think, a very strong use of equivalence test. So we set up these examples with this around 0, because it's basically just building off on the current practice, which is to test against 0. But you can use it much more flexibly than that. Okay, one thing about, last thing about justifying your equivalence bounds. Of course, wider bounds will make it easier for you to conclude that the effect is sort of equivalent, right? It's easier to fit a confidence interval into something that is further apart. Of course, it also means typically that you will there's less that you will learn less of it. There's one example, and Quintana has a analysis of results that looked at intranasal oxytocin on several social behaviors and effects. So this is a whole literature with lots of quite small studies and lots of, I guess, mostly file drawer effects that were non-significant. He looked at lots of those studies and reanalyzed the data to look at if you can basically see if the effect is really smaller than something meaningful. And so he applied equivalence tests to this literature. So what you can see here, the result is the pink shaded area is always the equivalence range. And in there are the confidence intervals. And what he did, I think he used an equivalence range based on what the study that he was reanalyzing had 80% power to detect. And then looked at if the confidence interval fell between those bounds. So looking at the power of the study itself is a bit tricky for weird philosophical reasons that I don't have time to go into, but if you just look at this, and you look at the x-axis, which is Cohen's d, look at this is almost minus 0.9 and plus 0.9, something like that. So it's almost plus or minus Cohen's d of 1. So these are huge bounds. This is really wide. And you can see that even with these wide bounds, there are quite a few confidence intervals that are not equivalent, that overlap with 0 and with this super, super wide bound. So basically, all you can learn is that there's so little information in this data, it's hard to conclude anything. You can't even reject the hypothesis that the effect is larger than a Cohen's d of 1. You also can't reject that it's 0. So like you learn very little, and if you can, so let's say, I think this is an example where there's no overlap. So here, what you can conclude is the effect is somewhere between minus 0.9 and plus 0.9. And I think in most cases that would be quite unsatisfying, because it means, okay, like you can exclude things that maybe a priori were implausible in many psychology studies. So for some studies, this can be a totally plausible prediction. So just to illustrate that it really depends on what you test against, what you learn. If the bounds are very wide, and you find something as equivalent, it just means you can exclude extreme effects. But it still means that the effect could be large, or it could be moderate, or it could be small, or it could be tiny. All you said is it's not huge. So that to keep that in mind, I'm trying to come up with sensible decisions. I think, yeah, so as take-home message, if you only test against point null hypothesis, your research hypothesis is not falsifiable. If your research hypothesis is not null, if it's anything but 0, because if you can't reject the null, it could mean all sorts of things. It could mean that there is an effect, but it's just you didn't have the power to detect it. So you could say, maybe I'm still right. Maybe I'm still right, and you will just never be proven wrong. Equivalence testing is one way to specify and test your research hypothesis. So your bound can just be one way for you just saying anything more specific than it's not 0. There are other ways to do this as well. This is just one. And I think I forgot to mention this in the beginning. The method equivalence testing is not new, so it's not like we invented this. It's quite an old technique. It's used commonly used in medicine and biostatistics. It's just that psychologists, for some reason, haven't been used to using this, and Daniel was set to change that and to walk psychologists to the water, basically, and get them there. The result of an equivalence test is only as meaningful as your smallest effect size of interest, and thus should be pre-registered like all hypothesis tests, presumably. So if you first look at your confidence interval and then you draw your bounds around it, you lose the error control, which is the nice thing that you would want to do, why you want to do it in the first place. Because every confidence interval ends somewhere, except the 100% confidence interval. If you try to define your smallest effects as of interest and you find that you really struggle, and it's extremely, extremely difficult, and I have now that this paper has been out for over a year and people ask us for advice to do this, I can see how difficult it really is, even for people who are very smart and very sincere about this. I think actually in many cases that just shows that we might not be ready for testing hypotheses. So if we have no way of specifying our prediction in a way that makes it testable, then maybe what we need to do is not trying to come up with arbitrary ways of testing it, but to learn more about what we're studying in order to be able to make a precise prediction at some point. Right? So this can also be a clue that maybe what's needed is more exploratory research, that more theoretical work needs to be done first. Which is, I think, quite neglected in psychology, sadly, but it would be great to change that. Okay, so that's it for now. Do we have time?
Yeah, we have time.
So we can do questions now. I can also, if people are interested, show 2 examples from my own work, how I justified the smallest effect size of interest, but maybe questions first.
Yeah, well, first of all, thank you very much. We have quick questions from the floor, if anybody has any questions. We usually shout speaking, here we go.
Yeah, I'll step into the
Yeah.
Thanks for a very nice talk. As a sort of statistical ignoramus, my sort of go-to method for deciding if something's worth bothering about is whether it's more than one standard deviation either side of the mean. So, if I want to know if someone's significantly more intelligent than average, if they're within one standard deviation of the mean, they're not really, because there's error in the test. So, is that kind of roughly what you're talking about?
Well, it really depends on what that means for your subjects. I can't give a blanket statement. I mean, if you do this for group comparisons, then one standard deviation is a coency of 1, right? So in most areas of psychology that I'm familiar with, this would be a very big effect. And people would be very interested in finding smaller effects than that.
No, I'm just talking about an individual. Say you're in an occupational testing setting.
Oh, right, yeah,
you get
right.
someone IQ test and they score 114 and the ST is 116.
Yeah, that's an interesting question. I guess there are ways of doing that. We've been thinking in general about if you can find the smallest effect size of interest based on the reliability of your test, right? If you can say like the test can only reasonably pick up things of this magnitude, for example, that's relevant to test, so that the theory can only is only as basically prediction is only as precise as the reliability.
Yeah, well, you'll have all that with Cronbach's alpha and stuff. That's all in there.
So in general, it's a good question. We haven't thought about cases like that where it's about diagnostics.
Yes, we do it here with, for example, if you need to recruit depressed people, let's say, and you have a score and you have to see are they significantly depressed or not, you know. So
it should work the same way as you usually would say it's significantly different. You should be able to do it the same way, just the other way around.
Okay, thank you.
Thank you. Really interesting. I have a question. I think it's mostly just coming from I need to read the paper in more detail. So you can just correct me where I'm misunderstanding things. So first of all, when I was listening, we had the image we had a million large sample size, and we have very small constant intervals of both. And I think so that's showing that I sort of realize that sometimes you're going to show that either the effect is sort of significant, but it's too small to sort of care about, or rather, so one outcome of your equivalent test is that you can't rule out that it crosses the line, and therefore you can't say anything about the upper bounds of that, or it doesn't, and therefore it's in that range you don't care about.
Yeah.
And so my initial reaction was sort of like, so what has that got us? Then thinking through, okay, so it does make sense that we're essentially, it's the opposite of what we were originally set out to do, is we're constraining the limit of what we wanted. And then I think one of the last things you said about choosing those boundaries, and I thought, okay, why don't we just report them and say, instead of sort of making it into a hypothesis test, that we want yes or no, we can confine our estimate to a certain range. Why don't you report the range, the effect size, or the that we can constrain it to? I think that's what you, in one of your last points about sort of, not doing 2D tests and that kind of thing. So I need to read some more, but it was very interesting.
So basically, if I understand you correctly, it's the question if you can't just estimate the effect size and report the confidence interval, for example, to see where it is. Of course, you can do that. It's different from this because it means you don't test. Like, you don't have a test with a fixed error rate. And that is basically, if you want to do, like, the nice thing about equivalence testing is if you want to test a hypothesis with a certain sense of the evidence that it gives you for the error rates, that's a nice thing to do. Estimation is a different approach in that sense because you don't have error rates, you don't test the hypothesis. I think I agree that it can be useful in many ways where you are not yet there where you make a prediction. Like, you don't say, I don't know what the effect should be. I don't know what this theory or this hypothesis really says. I just want to know what the world looks like. Then estimation can be a good approach, and just trying to be as precise as possible, see what it's like, and then, and I think that can sometimes be all you want. Sometimes that can be a step to building a theory on it. So it's basically just a slightly different case. And I think that it's probably underused in psychology. I think papers are sometimes written as if people just want to look, but then they always test hypotheses because that's what we do.
Thank you so much for that talk. I'm sure you're aware of the whole p-hacking stuff. I was wondering if that would also apply to the equivalence
Yeah, exactly. So yeah, yeah, that's a good point. So it's very easy to just set the bounds post hoc, right? Or just tweak them post hoc. We didn't actually mean that. And yeah, that would introduce the exact same problems as with null hypothesis testing, picking different ways of operationalizing things. And so my opinion is that the hypothesis test should always be pre-registered. That's my opinion. So yes, it's a problem.
I have a question. Recently there's been questions raised about Bayesian analysis and people just using default priors.
Yes.
I think this is because people find it difficult to completely remove themselves from using benchmarks and arbitrary effect sizes. Is there anything unique about equivalence testing that goes against that, or does it still have the same issue where you could just have people moving to equivalence testing but using, say, a minimal effect size of, say, Cohen's d of 0.2 or something like this? Yeah. Or do you not care about that? It's just that it's getting the critical mass to move over towards null hypothesis significance testing, say.
That's an excellent question because I do worry about this. And actually, at least both of these papers are getting cited quite a lot, and I'm dreading to look at the way in which they get cited actually. And Daniel actually had an earlier paper already, and we looked at some of the citations of that one, and we already saw that people use the test in a non-ideal way, like with just benchmark effects basically. I'm not happy with that. I don't just want people to use this method mindlessly, because using any method mindlessly doesn't really get you anywhere. I mean, you can hope that they use it mindlessly and then they notice some things in this process and they become more mindful over time. But I'm a bit skeptical about that, because people have made this claim for many methods, only introduce confidence intervals and force people to report effect size estimates, and then they will start to appreciate the effect sizes and will be interested in them. And I don't really see that happening, right? So it definitely is a risk, basically. So my opinion, and the same goes for the use of base factors, as you said. I think actually this paper is maybe nice to look at, because we tried to apply base factors and equivalence tests to the same data for a number of examples that we got from the literature, and you see that both times it's about what would be a sensible thing to test, right? Like what captures the spirit of the study, basically. And for base factors, it will always be a bit different than for equivalence tests, but the more similar the justifications become, the more similar the results become as well. I think, as I said, hypothesis testing is sort of pointless when you don't have a hypothesis, really. And I think people don't have hypotheses more often than think. And it's a problem, and we're not going to fix this with this. And it will get misused. I think it's already getting misused. I think we need to work on other things to make people aware of that, and maybe say, actually, I think one thing that I'm more hopeful about is pre-registration. Basically forcing people to make all these specifications ahead of time when they don't yet have the data, because they often find it so difficult. And maybe that helps them realize that they need more information before they can get there. They need to do more work before they can get to this precious test at the end, basically.
I mean, one idea I had was, I'm not clued up about this really, but I know that with JAS, when you do Bayes, it does a robustness check, which is kind of what you were mentioning about the size of interest, where you can just do a kind of sensitivity analysis to see the range, if I understand it correctly. So I think with JAS, it does a robustness check for Bayes, so you can just see just how robust the effect is. So you can look at a range of different priors, and if the same result persists, then you can say, okay, this result that I had is not necessarily due to the prior I used. It seems to be systematic. So I wonder whether you could do that with equivalence testing, where you just say, okay, we roughly know the kind of whereabouts our size of interest is, but we'll do a bunch of sensitivity analysis just to see how.
So you could. The thing is, that's that's more similar to just looking at the confidence interval, or just making an effective estimation, I guess. The thing is that it's difficult to compare the methods at that point, because with Bayesian analysis you have no error rate, basically. It's just about how you update your beliefs, theoretically. So it's a bit philosophically different. And then you can say, I'm just going to look at what if I had tested against other things, and how does that look like? And if whatever choices I make, it always goes into the same direction, that's basically equivalent as having a ton of data and having a super tiny confidence interval, where it's going to be easy to reject that. And if it's more vague, your base factor will depend more on which prior you choose. And that then again is similar to having a wider confidence interval, seeing, well, it depends on where I put those bounds. But in the frequentist framework, if I try out different bounds, I lose my error control, basically. But I mean, you can look at it and think what would have happened otherwise. It's just not the same test, basically. But the idea is just learning from the data is, of course, the same. You can always look at the data and learn from it and see what you believe, basically. And more data will always be less sensitive to specifications.
Time. So we've got 5 minutes. So is that enough time to go through an example? If not, it's okay. We can break for coffee and tea and biscuits.
I think, yeah, let's give people a break.
Okay, yeah,
Probably.
sure. Okay, well, thank you again.